Hello and welcome back to Calculus 1. Last section of chapter 3 on related rates. What do we mean by related rates? Well, rates as a derivative. Do we know that velocity is change of position over change in time? So it's a rate, right? It's a fraction. Position divided by time. Now we're going to have multiple derivatives that are related by some formula, and we're going to use that to model the world around us. So let's start with the simplest possible case. Imagine an ice cube sitting in the sun, melting, right? Ice cube. It's a cube, therefore each edge, right, is of the same length. We can call that lowercase a. So A. Now, you think about it and you say, in time, as this cube sits here on the sun, we have multiple concepts diminishing. Volume, because it's melting. Immediately, because the entire object is getting smaller, the surface area of the entire object is getting smaller. Each of the edges, right, the sides, is getting smaller. Each one of its diagonals, whether it's diagonal of each of the faces or the major diagonal in the middle, they're all getting smaller. Everything about that cube is getting smaller in time. So let's observe volume. That would be one of the most frequent cases. So volume of the cube is a cubed, right? So that's the volume of the cube. And now you are observing the volume of the cube as it's changing in time. So I'm going to take the derivative in respect to time. What I get as a derivative of v is 1, but then followed with the chain dv dt, because I took the derivative of v in respect to t. Remember, the implicit differentiation is teaching you that you are supposed to follow with a chain every time when your variables don't match up. So volume clearly doesn't match up the time, therefore dv dt is there. Right? So the derivative of v is 1, like derivative of x is 1. But you have to follow with the chain dv dt. On the other side, derivative of a cubed, a is a variable because it's the length of the side and it's shrinking in time. So a is a variable, therefore 3a squared, and then we have dA dt. Now this particular formula here will be called related rates formula. And it's a model which tells us the relationship between the shrinking volume and the shrinking side. And it's related by this 3a squared in between. So dv dt is actually the amount of water that is flowing off of the ice cube, which you can calculate how much. The loss at the side, you can also calculate in time. A squared, right? So you can actually go to the lab. You can go to our chemistry lab and verify this instantly by observing the ice. I mean, you have patients, right? Observing it melt real time. Note that a squared is always a positive value. So if I pick dv dt to be negative because it's melting, then dA dt would be negative, which also makes sense because the length of the side decreases. And that is the rate of change of a side, of the length of the side, negative for decrease, positive for increase. So now to understand this, this will be the rate of change of volume in time. That's what it is. The rate of change of volume in time. And the units must be volume over time. So inches cubed per minute, right? And this one, blue, and this one over here is the rate of change of the length of the side in time. And it has units of length over time. So inches per minute, inches per hour, inches per, right? So that's the way we know what these values are when we read the word problem. The volume is decreasing at the rate of 1.3 cubic inches per minute. Oh, great. That's dv dt because I have inches cubed per minute. So thinking about this, dv dt would be in, let's say, inches cubed per minute. So it's some kind of length cubed per unit of time. That's what it is. You have dA dt. Could be, let's say, inches squared per minute. That's length squared per time. dA dt, inches per minute, that's the length per time. Anytime you have units, right? You have the word rate, the units can quickly tell you which rate you have to write, because units of time are seconds, minutes, hours, days, years, months, right? Those are the units of time. Units of length, where we have feet, inches, meters, millimeters, centimeters, right? Light year is a unit of distance. We all good on that? Light year, it's a unit of distance, not unit of time, unit of distance, because it's the distance that the light covers in 1 year. It's very, very long. Great. So now, there are two-dimensional problems, three-dimensional problems. You will be looking at the geometry of the problem, and then you would write the formula, differentiate the formula in time, plug numbers in, right? And let's just do a whole bunch of problems. We don't learn any new methods or techniques here. This is applied section where you need to be able to use implicit differentiation to come up with a formula and then just plug numbers in. So we're not learning any new concepts. It is just let's do as many problems as we can. So let's go and talk about oil spills. Hashtag BP. In time, the oil rig will spill, right? Something goes wrong. It will spill this crude oil everywhere, right? And it goes in concentric circles, right? It's getting larger and larger and larger. The longer you wait, the larger cleanup you have. So you can calculate the rate at which the surface area of the spill is progressing. The oil and water, they separate from each other, they don't mix. So the oil floats on top and just need to scoop it up, but it's just a lot of it. So you have to catch it while it's not too crazy. Now for a circle, we have formula for area as pi r squared, because you are talking about the amount of water that it's on the surface, right? And it's in a circle and it grows out as a circle. Then we take the derivative in respect to time, because we want to see the change of area in time depending on the change of radius in time, because notice that as the radius is getting larger, the area is getting larger. So they grow together. So my dA dt is equal to 2 pi r dr dt when we take the derivative. Derivative of r squared is 2r, put 2 in front of pi, and then because we took the derivative of r in respect to t, dr dt is the chain that follows. This is your related rates. So in general, in a second step, you should already have your related rates formula, and then you might have to go and, chase other numbers around. But so now I have the change rate of the area in respect to the change, right? Rate of change of radius in time. As one is getting bigger, the other one is getting bigger as well. So an oil rig springs a leak in column C's. The oil spreads in a circular patch around the rig. If the radius of the oil patch increases at the rate of 30 meters per hour, if the radius increases, so that has to be dr dt, because they give you 30 meters per hour. This can't be volume, because it's not meters cubed, it's meters. How fast is the area increasing? So area, see the word how fast. How fast? You do that in time, right? How fast can you get somewhere? Right? How fast can you answer the question? How fast can you wash your hands? So when you ask question how fast, you are looking for how fast, which is something in time. That's what we measure how fast in respect to time. And then some people are faster than others. So we are looking for how fast is the area changing. How fast is the area of the patch increasing when the patch has a radius of 100 meters. Radius flat, 100 meters. Great. I have everything for my formula. I am looking for dA dt, so leave it alone. 2 times pi times 100 for the radius times 30. This is 600 pi. Of what? Potatoes? It's meters square per hour. Meters squared per hour. And that's the answer. So how fast is changing? It's changing at 600 pi. That's about 1800, almost 2000 meters square per hour at this stage. Important calculation, right? For environmental scientists, for instance. What else can we do? Is the airplane problem? Yes. Let's talk about an airport. There's an airplane coming in from that side. There's an airplane coming in from this side. And there is a separation in between them. This separation, capital D. Now, if the plane on top is flying due west, it will be flying this way, right? And the plane on the bottom is flying due north. Aren't both of these going towards the airport? So when both of these airplanes are at the airport, what's the distance between them, right? Hopefully you won't say 0, because the distance is very short. So this distance changes as the two airplanes fly in. The distance is changing. Would that be an important piece of information to know if you are in a control tower? Yeah, you might, right? You might want to know that. At which rate the distance between these are closing. Why? Anyone? So they don't crash, exactly. Let's take a look at the busy skies. That's Norway. Let's go to the United States. That's Canada. There we go. Perfect. Ah, there we go. This is live. It's a little bit busy over here. There's New Jersey. Ah, there we go. There's New York. Look at that. You think there's Joe sitting somewhere on the side, figuring out this by hand? You need to write a software that's going to untangle that. And it's not going to get buggy, okay? So, it's busy. And we want to know the distance and separation between each one of those pairs, plus the distances from every single airport that is closest where they can land in case of emergency, right? All of these kind of things. And we clearly let the software worry about it. Currently, 12,806 commercial. This website does not track military aircrafts, does not track commercial like a UPS and all that. This is just passengers. So you can click on any one of these planes and get the detailed info, scheduled to land, to right where it's going, where it's right, how far into the plane. And if you subscribe, you even have a little camera under the plane. You can watch what's underneath and so on. So there's a lot of cool stuff that this website provides. Now, they are offering cookies as well. Sure, please bring. So this is what the sky looks like currently. Now, going back to our problem, we are only focusing on two airplanes. We are going to have a distance x and a distance y as these two airplanes approach the airport. What is the geometry of this problem? Triangle. What kind of a triangle? Right triangle, right? Over here is the right triangle. Good. What are the formulas that we could use from the triangle? Which one? Pythagorean theorem? Yes, great. What else? What else do we have for a triangle? Law of sines, law of cosine. So we have all the whole spiel of trig stuff, right? Just writing a basic sine and cosine and tangent, right? With opposite over adjacent, right? Which could be of these sides. So we have the whole spiel of trig, Pythagorean theorem. What else do we have for triangles? Area, yes. 1/2 b times height. We have area equation. And then, what else do we have? Perimeter, very good. So now, in this list, we probably have about 10, 12 formulas on a pile. Which one do we choose for the problem? We start by asking ourselves, do we need area? And we are not looking, because we don't care about this area here. We care about separation of the airplane. So we care about the length. Do we have any angles? No, we don't have any angles. That kills all of the trig right off the bat, right? So we have perimeter and Pythagorean theorem, right? Now, Pythagorean theorem is a good equation that connects the lengths of the side, and if I differentiate, each one of those lengths becomes velocity, which is another thing that we have, right? The speed of the airplane. So if I write that x squared plus y squared is equal to capital D squared, which is a basic Pythagorean theorem, right? Seen this in grade school. We can differentiate that one in time, and we get 2x dx dt plus 2y dy dt plus, equals 2d dd dt. And then all of these 2's drop. You divide both sides by 2. So looking at this, right? You don't get to write a mathematical formula or a physics formula or chemistry formula and disconnect it from reality. You look at these formulas and you say, okay, what do I have? I have distance x between the airport and the airplane that is on top, and I know that this airplane is moving in at the speed dx dt because it's covering distance x in time. So dx dt is the speed of the x airplane on top. The airplane on the bottom is covering distance y, therefore its speed better be dy dt. And that's going towards, right? Now, the speed between the two airplanes, as the airplanes move closer to the airport, the distance d is going to become shorter and shorter and shorter in time. So there is a speed with which distance d. And that is the one that we are actually interested in, because we want to know how fast is the distance between the planes closing. We're trying to stay away from the zero, right? Because zero is not good times for this case. Now, do I have the rest of the information? Yeah, because each control tower has the radar. Radar knows exactly how far each airplane is from the airport, right? So control tower has the distance. Well, also the pilot has the distance. X and Y is known, right? Now the airplane has a speedometer on it, right? So it's going to read 500, 600, 650 miles per hour. So dx dt, dy dt are known, x and y are known, and because you know x and y, you can know capital D. So in this entire equation, the only thing that you don't know is exactly the thing that you are interested in, and that is how fast these airplanes are approaching each other, because you don't want them to get to the distance 0. So you plug in that this one is 100 miles out, going at 500 miles per hour. This one is 300 miles out, going at 600 miles per hour, and then put in 100 and a 300 and calculate D. You plug that there, and you have 1, 2, 3, 4, 5 out of 6. You can compute the change in distance between. So the quantities that you get to plug into these equations are the quantities that you know, that you can measure in our reality around us. And as I said, the distances are measured by radar, the speeds are measured by each airplane, and then you can calculate the capital D using the basic formula, and that will give you this. You program that, right? Because it's this airplane, and then there are other 30 airplanes in the vicinity, and they all have to have a non-zero separation. Otherwise, right, not good. So one more time. Not so busy today. This gets to be much busier. This is just United States. Here's the border with Canada, right here. Chicago, right there. Pennsylvania, Vermont, right? You thought New Brunswick is close, right here. So Philadelphia, this is JFK, LaGuardia, and Newark. So obviously very, very busy around those. I'm not sure if I'm going to have you for Calc 3 or not, but just want to show you these. Do you see these paths? Do these look like straight lines across, right? They don't. It's curved path this way because the planet is round. Just making sure.
What does that have?
So the shortest distance on the curved surface is not a straight line. None of these planes would make it if they went straight across, because it's the ball, he has a belly, so going across that belly, it takes a long time. It's called the geodesiac, the path you take on a curve. Right, so this is the planet. Here's your equator. There's going to be a center somewhere, and you have 3 points. When you take the airport 1, you take the line through and cut through the center of the Earth. You take the other one, cut through the airport where you want to land. That creates a plane, the plane like the board, and when that intersects the curved sphere, it gives you what we call the geodesiac, which is the shortest line between the 2 curved points. It's never going to be a straight line. So only on the flat space, the shortest distance between 2 points is this. None of the geometry you learn so far holds on curved objects. None. What's the sum of the angles in a triangle?
180.
180. What's the sum of all angles in a triangle on a basketball? Not 180. All right? Because when you are on the ball, think about it, right? You're on a ball, you draw the equator, and you can go and do this on a basketball. If you have a ball at home of any kind, here's the North Pole. If you walk straight down, you make a 90-degree turn, and you walk for the quarter of the ball circumference, right? And then you make another, and you walk straight up to North Pole, there will be another 90-degree angle. So that's already 180 for this triangle. Now all of these lines are perceived as bent because it's on the surface of the ball, but it's a straight line. And what happens on the top? Well, remember that I went a quarter of the ball. So if you look at the top where the North Pole is right there, to get a quarter of a circle, L over 4, which is L over 4, what's at the North Pole? So sum of all angles is 270 in this case, all right? I know. This is the basics of hyperbolic mathematics that you need to learn in order to understand general theory of relativity, what Einstein did, and all of these kind of things. So, when it goes on curved path, it's good, right? It's time to panic if you see, right? If you're in an airplane, you see an airplane going this way, yeah, time to panic. You're not going to make it. You'll probably end up like right there. That's it. That's it. No fuel. All right. So that's the airplane problem. One of my favorites, and you get to see a really cool website. So. That's the website. I use it every time when I need to pick up someone at the airport at the, let's say at Newark. I actually wait until this website tells me that the airplane landed. Then I leave my house. Because it takes me about 35, 40 minutes to get there. By the time pick up the bags, by the time to go through the customs and all of these kind of things, there's no reason for you to spend $100 on parking. So, right? So that's a really cool way to save time and money. It doesn't work actually. This doesn't work if you go to JFK because your commute to JFK could be anywhere from an hour to 7 days, depending on traffic. So that would not work. But for Newark, one works 100% of the time. All right, great. So this is our problem with two airplanes. As I said, you learn linear algebra, and then you put all of this in the matrix, and you figure out between each one of them and so on. But the geometry of this problem was a triangle, the oil spill was a circle, the ice cube was a cube. So you always look for some kind of 2D or 3D geometry. You will write the formula for that geometry, and then you will differentiate that formula using implicit differentiation. You will get a whole bunch of derivatives, 2, 3, 4, and it's called related rates because each one of these derivatives is a rate on its own. So you will get a whole bunch of them, and they will be what we call related by the formula. Now, in our case here, dx dt is going to be negative, right? Because you are closing the distance towards the airport because it's a velocity. Speed is 600 or 500, whatever, but it's going towards the airport and it's closing the distance, so it will be negative. The other one would be negative as well because it's again closing the distance. And then when you add a negative number and a negative number, you get another negative number, and the distance between two airplanes is closing as well as they're getting closer. So, you know, in terms of signs, all of that should make sense because, right, we use mathematics to describe the world around us. All right, what else cool can we look at here. Let's talk about drinking soda from a soda can, right? Another one of the problems that you can, right, take out and talk. So you have a soda can, which is a cylinder. You're going to have the place where you put a straw. Straw goes in, and then you drink. You take a sip. Now, what happened? No coffee. What? So you have liquid inside. I know I used blue to represent water. I know that you don't drink that stuff from the can, or it's usually some kind of poison that it's either black or whatever non-natural color, right? Orange. So as you drink, what happens with the liquid inside? Decreases. What decreases? The volume of it decreases. What else decreases?
The volume of the contents inside, obviously.
That's the volume. Sure. Volume decreases. What else decreases?
The weight decreases.
The weight decreases, okay. Not what I'm looking for. So.
The air increases.
The height of the liquid decreases. Thank you. Right? Because the soda can was full all the way up to here. Right? You started drinking and the height goes down. So we have the height of the liquid. We have the height of the liquid, and we have the volume of the liquid. We also have the radius of the can. Now, this is something that you can actually do when you're out because you have access to Google through your phone. For cylinder, what is the volume for cylinder? Pi r squared times height. Very good. Now, we're going to cover all of the volume formulas in group of 3. So you will all know this. If you don't know it now, you will all know it in about 15 minutes. Okay. Please pay attention now. This is life-saving. We said volume is changing because you are drinking. There is less drink inside, right? Like less liquid. So volume is definitely changing, is decreasing. We also said the height, right? Is radius changing? No. So here I'll write in blood. In this case, radius is constant. So in this case, radius is constant. Now, simple Google search will tell you what is the radius of the soda can. And believe it or not, a simple Google search will tell you what is the size of the average sip from the can. Average size of the human sip, given in cubic centimeters, right? The volume. So you know the rate at which you are losing volume, and the height you can measure simply by, like, you can use the straw as a dipstick, and you know how much of it's wet, it's how much height you have. So now I have the formula. I get to differentiate this in time. Pi r squared h. Keeping in mind that this time around radius is constant, and if radius is constant, we just get to copy it, right? So dv dt is equal to 2, no, sorry, lied, pi r squared dh dt. I did not take the derivative of r because it's constant. And it's not 0 because it's multiplied into h. So this entire thing here now behaves as just 3x, where h is x. All right? You can take the derivative of that. You can Google this. You can Google that. And you just plug the values in. And you can see how fast is the height draining as you sip. So now when you're out and someone says, what do you know? You say that you can calculate the rate at which they're drinking. Now, would this hold forever? The answer is clearly no. Because you can drink out of a cone, which is cut, so it looks like a cup, right? But that's a cone, that it's unfinished cone, right? Just cut this piece off, it's just a regular cup, right? Now, in that case, is it going to be the same as the above? Clearly not. Why? Radius is changing now. Yes. So you have the volume formula, where you have volume is a variable, radius is a variable, height is a variable. Radius times the height. So when I take the derivative, what happens? Yes, so, right? So let's take a look at the cone. Now, for the cone, instead of doing the cup, we can take a look at engineering problem where you have a conveyor belt, right, with, let's say, sand or gravel or corn, doesn't matter. Some stuff is coming down this conveyor belt and it's just falling down onto a conical pile, which becomes larger conical pile in time. Right? That's all. So you have sand coming in, gravel coming in, corn, whatever. It's just falling on a pile, creating conical pile. You all should know what that means, right? Now, the amount of stuff that it's coming in is volume in time, because you are going to let a cubic meter of corn, right? Okay, the back of the truck, right? Take a big truck, dump truck. I don't care whether you have sand or corn or whatever you have inside. You are going to dump that much onto the conveyor belt, and then it's going to start coming in off of the conveyor belt onto the pile, so you can measure the volume that it's coming in. What else can you see? You can see the radius over here. Then there is a height, age, and both radius and height are changing according to dh dt and dr dt. Now, height is very important, because if you just leave this stuff to pile it up and pile it up and pile it up and pile it up, eventually this cone is going to touch the conveyor belt, right? And then it's going to just accumulate stuff on one side, and nothing will be going this way. And then the stuff will start accumulating on the conveyor belt, making it heavy, breaking it. Now, these things are $1 million installations, right, in businesses and so on. So maybe you want to design something that will shut it off. So you are going to measure the height in time. And as you're measuring the height in time, you will know automatically when to shut it off. Now, if you say, well, we can just use the photocell, and well, no, you can't because there's too much dust. It doesn't work, right? So what do we have now? What's the volume of the cone? Very good. 1/3 pi r squared times the height. And if you are to differentiate this, you will get dv dt is equal to pi over 3 times, and now you have copy the first, derivative of the second, plus copy the second, derivative of the first. So now you see in this related rates formula, you see 3 different rates. They all depend on each other. As volume increases, right, of the entire pile, and it's increasing exactly by the amount that it's getting off of the conveyor belt, right? If you dump corn, corn doesn't multiply on its own, right, to make it grow faster. It's exactly the amount that it's coming off of the conveyor belt, which is what you can compute. On one side, you have a rise in height, dh dt in time, and the change of rate of radius, meaning the pile becoming fatter and fatter in time. Now, usually we don't have all of the information to calculate here, so we look for extra relationships in that are given to us in a text of the problem, or you just look for those relationships if you're out in the field. One of those relationships would be similar triangles, right? If you have a smaller cone, and now this is just a half of the cone, like half of the cross-sectional layer section. So you have overall height h, and your lower height h, and your lower radius r, and your large r. So now, what small height is to big height, it's the small radius to the big radius. That's the basics of proportionality. Now, these capital letters are usually given as numbers in a problem. So now, if you are looking for heights, you will solve that the little radius is equal to r over h, which is a constant, times the height. So I'll just put here r and h constants, r and h variables. And this is important because you have to differentiate this. It's not just enough to replace each one of these r's with h and walk away. You also have to eliminate the r dt because you are looking for the h dt, and you never have all of them given. So when you take the derivative in respect to time, you will get dr dt is equal to r over h is a constant, and then you have dh dt. So plug in up there. And then you are effectively killing r's everywhere, and you just have dv dt and h dh dt to worry about. So some relationship between H and R is always given to you, or you are expected to find it in order to solve the problem. And this problem is far more complicated, obviously, than the previous one, just because now radius is no longer constantly. Radius is changing depending on how big the pile is. Now you can do this, you can drain the water, you can, you know, cone is a cone. Cone is a cone. And as long as you know the formula for volume, you should be able to do it. So now, here is the $1 million overview of volume. You can mail the checks with the attention of my name. We have 3 categories to worry about. Category number 1 are prism-like objects, which would be your cylinder, your cube, your rectangle, which is also a cube. Well, I mean, cube is rectangle with all sides same. The volume for this is the area of the base. So any type of a prism. I'm going to draw one more, the one with a triangle, like this. So it's area of the base times the height. So if you know what base you have, whether it's a triangle or a circle or a square, rectangle, whatever you have, and if you're able to calculate that area of the base, then just multiply by height and you are done. The second, so these are prism-like objects. In the middle, I call them spiky objects. You have your cone, you have your pyramids. So if they go into a spike and the volume is 1/3 area of the base times height. So for the cone, area of the base was r squared pi, and then times the height, and because it's spiky, 1/3 in front. For the cylinder, it was the same formula without 1/3, because they both have a circle in the base, right? So spiky objects, 1/3, non-spiky object, a prism, right? No 1/3. All alone, in a category of its own, the perfect third-dimensional object. Sphere, a ball. With the volume formula, or 4/3 pi r cubed. You get to prove this formula when you go to Calc 3. Take spherical coordinates, 2 lines, you're done with this. So here are all objects that exist in 3D realm. You have to categorize those in 1, 2, or 3. If the problem says a spherical balloon is being inflated at the rate, great, volume of a sphere. A snowball is rolling down the hill, becoming bigger and bigger and bigger, like in a cartoon, until it smashes into a house, right? That's again ball, volume, great. They say cone, 1/3 immediately, right? This classroom is a box, so it's going to be the prism. So make sure you have a note of this. And as I said, as long as you're able to calculate the base, area of the base, and the base can be a circle, a square, a triangle, a rectangle, can be trapezoid, can be right height, whatever. As long as you know, what's the area of the ellipse? Right? So in mathematics you have these, you have the symmetry at all times. The things work out. So if you have a square and a rectangle be in the same family, where square is a special case of a rectangle, they are the same, right? Just square is just a special case because it has all sides the same. They all have 90-degree angle, the two parallel sides, everything is the same. They have the same formulas. The formula for area over here is a times a, which is a squared, and over here is a times b. Well, this b, in this case, is another a. Well, in that sense, what is a circle? Special case of what? Of an ellipse. Great. What's the area of this puppy? Pi r squared. Okay, I'll draw one r over here, and I'll draw another r over here. So pi r squared. Great. So now for ellipse, I get to put the major A and minor radius B. What's the area? What is it?
Pi AB.
Pi AB. Nice. Exactly. Pi AB. Now can we connect all four of these shapes? It should be. A, R, A squared, R squared, A, B, A, B, A, B, A, B. You see that? You get to take this circle and inscribe it in this square. You get this ellipse, inscribe it in the rectangle. Now, what are the differences? A squared, R squared? What is the only difference? I can change this into A squared. What's the difference between the two formulas? Pi. So what is pi doing? Yeah, pi is rounding it off, right? Because as soon as I put pi over here, it becomes the formula for area of the circle, right? So the pi is going to make it round. Now you go and you apply this in other situations later on. I don't know how to know what teacher. Just walking, it's like, oh, I have 17,000 formulas to remember. No, 3. Right? That's all. 3 formulas. Move along. Great. What else can we talk about? Can we make some more money? Oh, yes. Let's make more money. This might be our last problem. We'll see. Maybe we get to do something with the sphere. So the last problem, they have a different scenario. I like to do this. Oh, you can't see. All right.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
Perfect. I'll just go, let's say right here. Great. No, I don't like it. Okay, good. So there was one camera, there was a second camera there, right? There's a third camera. What's the problem here? Can anyone tell me? So this is camera number 4. And camera number 4 is finally working. All right? So we don't have to have a camera number 5, and camera number 6, and camera number 7. It's not centered. It's shaking. Out of all of the engineering in the galaxy, right, that this man did to actually return the rocket and park it upright, right? Can't figure out to design a system that is just going to, right, record this as it goes up. So let's design that real quick, right, in this class, and then you go make that proposal, right? Maybe land a job over there. Well, if you have a CDO, I mean, you know what CDO is, right? It's OCD in a correct order. All right. So what do we have? We are going to have a little bunker for our camera, the launch pad, this is my highly sophisticated rocket. That we are going to launch. It's called NIC-X. Okay? So known as NICS. And that rocket is going to launch straight up. You all have seen the... Okay, we'll do that. Let's install the camera. This is our high-tech camera for 1927 on a tripod. And there's this elbow here. This camera can rotate. I'll call this angular velocity omega. And right now, the camera is pointed directly at the rocket. Remember that the camera has the right range that it's shooting. So it's enough to represent that range with the middle line, shooting at the camera, shooting at the rocket. And then eventually the camera is going to rotate and, you know, catch the rocket as it's going up. I don't know, put the camera reasonable amount of feet away so it doesn't get melted by the rocket launch. How many feet are we going to move the camera away from the rocket? 1,000 feet. Thank you. 1,000 feet there. Remember that I am concerned with this angle here because for those of you that did not cover this in physics, angular velocity omega is change in angle in time. This is called angular velocity. So what I'm designing is I'm after a formula that I'm going to program into the controller, and that controller is going to take the input variables, compute that formula, and send the electricity to the servo motor, which will turn the camera up. Now clearly, at the beginning, remember that we had those 3 cameras that switched quickly, and then the 4th camera was kind of following a little bit, the rocket, right? So in the beginning, when it starts going, it has to start going fast, right? And then it's going to slow down and slow down and slow down, right? The distance, right? As the rocket is not getting smaller, right? Is the perception of the rocket is right because it's further away. So so we have this. Note that on the video you have the altitude box all the way to the right in the telemetry. Do you see the altitude box? That's your height. You know that at all times. Yes, there it is right there. And as the rocket is going, you can see the height and you also see the speed. Can anyone tell me what is this speed of, let's go with 4,500 kilometers per hour? What is that in miles per hour? Just do a quick conversion. Miles per hour. Now we need to transform this into, we want to kill a mile and want to, oh sorry, we need, this is kilometers per hour is given, so we want to kill the kilometers and leave it in the miles. Now 1 mile is 1.6 kilometers, so we need to divide this number by 1.6. Huh?
I mean, yeah, I was just confused because it says 0.
Oh yeah, no, yeah.
Yeah.
So what is this calculation of 4,500? 4,500 divided by 1.6. How much?
2,796.
2,796 miles per hour. And yeah, it's gonna go. Are there really this many commercials in this, the YouTube thing? All the time? There we go. 26. So let's do this one. 26,100. 26,100 divided by 1.6. That's the speed of the rocket, eventually.
16,312.
How do you feel when you get the ticket that you're driving 80 on 65, right? You're going 15 over when this rocket is doing 16,000 miles per hour. Isn't that cool? Like, don't you feel insignificant? I do, actually, right? It's like, you were going 15 over. Like, really? How about that space launch, SpaceX launch? Anyway. Oh, no, I wanted the tablet. Great. So now, let's just write all of this stuff. What is my geometry here?
Triangle.
Triangle. Great. I clearly need that angle there, so what are we using? Trig. Perfect. Right? I'm not going to use area because I'm not coloring this. I don't care about Pythagorean theorem because I don't care about the distances. So I care about the angle. So the trig. And which trig function is going to connect these concepts here? Tangent. Very good. So tangent theta is equal to opposite, which is the height, divided by 1,000, which is our, right? And I need theta, so the derivative immediately of this in respect to time. The derivative of tangent is? Very good. And then we have d theta dt. There it is, d theta dt. That's our omega. That's what I need, right? Is equal to, on the other side I have 1 over 1,000 and then dh dt. And what's this dh dt? Which is? Change in height is 100% correct. I just want to know what it is here. What is the change in height? Speed of the rocket. Thank you. Do we have a speed of the rocket? Yeah, on a telemetry, there is a speed, right? That's your dh dt. And then altitude, that's your h. Perfect. So now we are going to ship this secant squared to the other side because we need d theta dt alone. Secant squared on the left becomes cosine squared theta on the right over 1000 dH dt. Right? We all cool with 1 over secant squared is cosine squared? Nice. Now, the only thing that I need is to get the cosine theta from my triangle, because I am not putting in the theta as a raw input. All I have as a raw input is the height of the rocket, right? So in my triangle, theta 1000 and the height, my cosine theta is going to be this value here, which is hypotenuse, right? So 1000 divided by the hypotenuse, and the hypotenuse is 1000 squared plus h squared. So divided by 1000 squared plus h squared. So my d theta dt, that thing, let me write it in blood over here, that's my omega, that's what I'm looking for, is equal to 1000 over square root of 1000 squared plus h squared, everything squared, divided by 1000 dh dt. And now you use algebra to simplify this, because you don't want to have unnecessary mathematical operations. Right? The less mathematical operations you have, the less calculations computer needs to do, which means that your software is less buggy, works faster for the same, right, hardware and so on. So d theta dt, and now you apply the square. When you get 1000 square, one of the thousands will cancel with this one. This is over 1 over here. So what do we get? We get 1 times 1000 squared, so 1000 on top. The bottom will have 1000 cancels with the other one. The square root dies for a square, so it's 1000 squared plus h squared dh d theta. dt, I mean. So now, that's your formula. This is the formula that you put on a controller, and from the telemetry, you pick those two variables, you stick one over here, you stick the other one over there, that's the speed of the rocket, that's the height of the rocket, and as you feed those in, computer is calculating the angle speed, right, to turn the camera. And it goes really quick. When the rocket is still on the landing pad, right, on the launch pad, I mean, the speed of that rocket is 0. So you have the whole thing over here times 0. This is going to be 1 over 1000 in that case, because height is still 0. You get 1000 divided by 1000 squared, so that's going to be 1 over 1000 times 0 is 0, right? And then when you fire the rocket, immediately this starts changing, that immediately starts changing this, and that's fed, and there it is. So there's no Joe standing there, right, trying to catch, there's no shaking, there's nothing, it's just, you know, a motor that turns it. And this is the way you make money when you, as engineer. Can you pull this off? That's the question. Remember, you are designing things that do not exist in a team with other people. Remember when I asked in class, can you build this model of the phone? Next question, lower on a scale, can you fix this device if it breaks, or you go and get another one? And then lower down on a scale, can you use this device, right? Just like, oh yeah, I just unlock and I just push a button on the screen, right? This is current technology. Touch screen, the fingerprint thingy, right? It's current technology. Text, call, take pictures, right? goes online, play game, all of these kind of things. The next one, I don't know, right? This is where your engineering and stuff now that goes for biomedical, it goes for every walk of engineering. You are not going to reinvent the wheel. So the ability to do these types of things, to understand what physical quantities mean and how they all work together, to come up with a formula, which is the one that you are going to program into controllers and things to create new devices that do not exist. Now, things are very complicated today, so you work in teams, but you have to be a productive member of the team, right? Which is what we have for your labs, right? Few of you in a group, if everyone contributes, everyone is happy. Now you can always, carry someone through the whole thing, right? Just get them to pass. But do they actually ever get to be the part of a team that designs a new processor for a new phone or designs whatever piece of engineering? So that would be the problem. And then, as I said, in general, the biggest hurdle is figure out what geometry you have, figure out which formula is the one that solves the problem, differentiate that formula, be careful which letters are constants and which letters are variables, because you saw the two examples, the soda can and the cylinder and the cone, where the radius was constant in one and variable in the other, because they behave differently, right? In a case of a cone, we have to do the product rule because you had R times H as variable times variable, where in the cylinder, we just had R times H constant times height. There was no product rule because R was constant. So those are the things that you have to be careful. Make sure you know those three formulas. The sphere problem, right? There's a little house over here. The chimney, and there we go. We gotta get the door and the window. Put a little person over here. There you go, and a scarf. This is where you are. Bigger scarf. And here's a little snowball that you go, pew. Right? What happens? As every good cartoon, right? A little bigger, a little bigger, a little bigger, a little bigger. There we go. Exactly. What happened?
I think the scarf would be fine.
The scarf would be fine, yes, yes. Unless you start this one with icicles. And I gave you too much direction already. So now what do we have? We have a snowball which grows in time, therefore the volume, which is pi r cubed 4/3 pi r cubed. When we differentiate that formula, you get dv dt is equal to 3 will kill a 3, so 4 pi r squared dr dt. Hopefully we understand the concept that as the radius grows, the size of the ball grows, and it all happens in time. You'll see it coming smooth. It's not a problem, right? It's almost twice the size, right? Smooth. It's not going to follow you. It doesn't have a propulsion system. It just goes straight. And you can calculate. So what is this telling me, the dv dt? The changeable, yeah, what does that mean in a physical reality? That's a wrong way.
How fast the snowball's getting big.
Yes, perfect. How fast is the snowball getting bigger, right? And this one tells us the same thing in a different way, because this one shows the growth in radius. How fast is the radius changing, right, as a growth? If the snowball is melting, that's negative, and then the radius is getting smaller, right? So that's negative as well. Remember that r squared is always a positive number, that's positive, that's positive. So these two are both positive or both negative, meaning it's growing or it's shrinking. Other problems that you find along the way, the spherical balloon for weather, you know, the people are screaming, oh, UFO, UFO, UFO. It's just a weather balloon. You inflate that one, right? And then you have the hot air balloon. Some of them are perfect sphere, right? So you can inflate that as well. And again, the rate, the radius changes and so on. And that's that for this. So.